Okay. And don't forget, quiz tomorrow, lesson 1, and then lesson 2 and 3 on Thursday. Yes? All right. Perfect. Today we're going to talk about, what are we going to do? Ionic compounds. We're going to predict formulas and write names for ionic compounds. And we'll draw some Bohr-Rutherford diagrams as well for that. All right. Now, you're going to have to fill in a few notes here, so you're going to have to pay attention a little bit here and see. But elements combine to form compounds. So I guess, what day was it? Friday, we went to the lab, yes. And we went in groups or whatever, but went to the lab and I showed you, for example, the first one I showed you was calcium, yes? And calcium had that like white coating on it kind of thing. And that's because calcium, of course, has 2 valence electrons, and it wants to get rid of those 2. And the oxygen in the air wants to gain 2 if it can, all right, to become more stable. So they kind of help each other out. So when you looked at that calcium that I showed you, that was actually calcium oxide that you see, because, like I said, oxygen has gained 2 electrons, calcium's lost 2. So that's that white coating that you see, and that kind of prevents it from further reaction. So it protects the calcium, right? For example, the lithium and potassium that I showed you, same thing. That's why we keep it in oil, because if lithium, you saw what happens when it reacts with water. So obviously it would probably get used up and change form, right? So we try to keep it in oil to protect it from further reaction, but you noticed when I pulled them out, they were kind of dull and not very shiny until I cut them open. After you cut them open, yeah, they're shiny. That's pure lithium, potassium, whatever, sodium. But on the outside, they've reacted with some of the oxygen in the air or any moisture in the air, and they've basically tried to become more stable. Okay, that's why most elements, quite a lot of them, we do not find by themselves in the environment. We find them in a combined form because they try to become more stable, of course. Atoms are stable when their outer energy level is filled with electrons. This is called the octet rule. So let's make sure we remember that octet rule. Okay. Oct, of course, means 8, so we're going to think 8. So most of the time we think 8, but recall that basically the first 3 energy levels are 2, 8, and 8. Right. The electrons in the outer energy level are called valence electrons. Very important. Make sure you know that. Electrons in the outer energy level are called valence electrons. And when an atom participates in an ionic reaction, it is losing or gaining of these valence electrons to become stable by having a filled outer energy level. So either we lose or gain electrons to have a filled outer energy level. Now this is for the formation of ionic compounds, of course. Okay. So an example. Okay. I'm not sure if you have this one here or not. I don't think you do, but that's okay. That's okay. Would magnesium lose or gain electrons? What do you think? Yeah, lose. And it's probably going to lose 2, yes? Okay, so if we can get rid of basically this one here, right, and this one here, if we can get rid of those 2, okay, now we have 2 in this energy level here, 2, and then we have another 8 here, yes? And now our outside energy level is filled, and it becomes more stable, right? Remember, when we lose those 2, we have 12 protons and 10 electrons now, because we've lost 2. So it's no longer neutral. It's not an atom anymore. It becomes an ion, yes? And we usually represent that with a magnesium, of course, and a 2+, yes? Representing the ion. Of course, if it's going to lose 2 electrons, they have to go somewhere, right? So perhaps we need some a non-metal of some sort to take those 2 electrons, yes? Okay. They just don't disappear just because magnesium doesn't want 2 electrons. It's not like, oh, I don't want you hanging around anymore. They have to find friends for those 2 electrons, right? They have to go somewhere. So just kind of keep that in mind. Obviously, when we're talking about ionic compounds, the idea here is it's compounds. We have to find, it's a give and take, right? Metals versus non-metals here. Let's see. Metals will lose electrons to become stable. Do you guys have that somewhere? Yeah. And it's usually called a cation, yes? And I think you have that there. Just make sure you underline that. So cations are referred to as metals, of course, metals that lose electrons. And non-metals that gain electrons, of course, are called dog ions, because that's the opposite of cat. Who's the cat people here? One, that's it. Who? Who does? Oh, well, are you a cat person then? No. Who's a dog person? Oh, yeah. All right. Those are actually called anions, okay? So the nonmetals that gain electrons are also known as anions, okay? Good? Okay. They don't usually, noble gases, why don't they usually participate in reactions? Somebody else? No, over here. Looking. Anyone? Come on. Because, yeah, they already have an outside energy level that's filled, right? So whether it's 2, helium, or neon or argon, they have 8. So they don't usually react with anything because they're already stable by themselves. They're the Mr. Bachek of the chemistry periodic table. Stable by themselves. All right. Obviously, you know, when we look at this here, there's some middle parts that we don't really usually talk about a lot because they don't share some of the same chemical properties. But when you look at a periodic table, for example, we know that group 1, of course, has 1 valence electron, yes. So this all has 1 valence electron. Usually these ones have 2 here. This would be in group 2, of course. And then we're going to skip like the 3 to 12 transition metals, but then we're going to go over to boron here. Those would have 3, 4, 5, 6, 7, and of course, well, 8 or 2 in that case, right? But that's kind of how it works, right? We skip kind of 3 to 12 there because they can vary there, transition metals, okay? So, good? All right. Patterns in the periodic table, that's where we are now here, of course. All elements in the same group or column have the same number of valence electrons. So if we're talking about group 1, of course, they have 1 valence electron. If they're in group 2, they're 2, right? And then we skip the middle parts there and we jump all the way over to boron and aluminum, kind of carbon and silicon, and then so on and so on. Okay. Okay. The transfer of formation of ionic compounds here. So ionic compounds are made up of metal and a nonmetal. Metals lose electrons while the nonmetals gain them. We already talked about that. Electrons are transferred from the metal to the nonmetal so that both elements have a stable octet. Okay. So we'll show you that in a second here. And we're going to show you how sodium chloride basically forms here, yes? These notes don't quite match up here. But, oh, my rings didn't work. Okay. All right. Well, that's okay. Let me do this anyway. For example, shown below here, you have the notes for sodium chloride, yes? So this is kind of what you're going to be doing here, and you already have that done for yourselves, but just so you know, we're going to start with sodium, of course, which has a what? 11 protons and 12 neutrons, which remember from last week, hopefully. 2 electrons, 8, and 1 more, yes? And that's the 1 electron, of course, that sodium would try to get rid of, 11 protons, 11 electrons. Along comes a chlorine, for example, 17 protons, 18 neutrons. We have 1, 2, 3, 4, 5, 6. Remember them, they start to pair up, 7, 8, 9, 10. And this one here has 11, 12, 13, 14, 15, 16, and 17. Okay? Yeah. 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 And then this here, okay, when these 2 atoms get close enough, basically what happens here is it's not so much that metals want to lose electrons as it is that nonmetals want to gain them. Okay, nonmetals really are the deciding factor here. They want to pull electrons towards them more, and the metals really don't put up much of a fight. So what's going to happen here is we're going to get a transfer of electrons. Okay, so when that happens, of course, this is how we get ionic compounds, atoms with a charge. Okay, so now that this has lost its electron, okay, we're going to write something like this here. So sodium has got 11 protons and 12 neutrons, and you're actually going to do this today here. You're going to do 2 here, and now we have 1, 2, 3, 4, 5, 6, 7, 8 only. However, we're going to put some square brackets around it now, okay? And we're going to notice that we have 11 protons and only 10 electrons, yes? Okay, because we've gotten rid of that one. So 11 positives and 10 negatives. Get a calculator out. The overall charge is +1. Calculator. No, you don't need one? Okay, you're AP. Probably don't need one. Okay, so we get an overall positive charge. And then, of course, chlorine here. Oops, let me actually just start with this here. Move this up here. There we go. Chlorine, 17 protons, 18 neutrons. Okay, 2, 8. Oh, that wasn't a great ring there. And 7. 1, 2, 3, 4, 5, 6, 7. Okay, and that was neutral, but now that it's gained that electron moved over, right? So now we get that extra electron right there. Again, we need some square brackets there, okay? And again, we have 18 negatives now, 2, 8, and 8. So add those up, 10 and 8 is 18. And 17 positives, so that's how we get the -1 charge, yeah. Okay? What holds an ionic compound together? So obviously you guys know that we have sodium chloride. Look, sodium chloride is probably on your supper table at night or dinner table or whatever you call it. We don't have salt on our table for some reason because my wife cooks so well that we don't need salt. I'm just trying to, maybe she'll listen to my video tonight or something. Probably not. Salt comes in solid form, so they're obviously stuck together fairly well. What holds them together? Sure, we'll go with that. Opposites attract, yes? So kind of like magnets, right? And it turns out that that's pretty strong enough to be in solid form, okay? Positive, negatives, and a bunch of them. Yeah, yeah, so it just acts like a magnet. Yeah. Okay. So you guys have that there. They use the little bold X there to represent the electrons there. Notice this use of the square brackets there, of course. Mine didn't turn out here very well, but notice the use, we're going to use square brackets and we're going to use some charges there as well, okay, to represent that, okay. The attraction of the two ions to each other is called an ionic bond, yes, okay. So you write that in there. Finally, we're down close to the bottom here. So the attraction of two ions to each other is called an ionic bond. Sodium chloride is called an ionic compound because it's made up of ions, charged atoms. Notice that the overall charge of the compound is still neutral though, yes? So even though we've gained and lost electrons and we have these positive and negative ions, it still overall is neutral, right? And that's because whatever you lose from the metal has to be gained by the non-metal, right? They have to work out. This is how we, of course, get these specific ratios, like sodium loses a 1 and chlorine gains 1 to become chloride, yes? Magnesium chloride. Well, now magnesium loses 2, but chlorine can only gain 1. So we're going to need 2 chlorines to go with that because we need to gain 2 electrons, yes? So that's where the formulas come from, okay? So the formula, the compound sodium chloride is made up of 1 sodium. So the formula would be what? Well, we're just going to take this nice and slow here, but if we have this and this, sodium loses 1, chlorine gains 1, okay? This is at the top of, actually this is probably at the very, well, that's at the very top there, yeah, on the back side. Sodium loses 1, chlorine gains 1, of course. We're going to do swap and drop. Do you remember that? Did you hear that before? Yes, no, kind of, maybe. Or, I don't know. Well, basically this one loses 1 and this one gains 1. So the formula when you write them together is NaCl, okay? I don't know what do you, help me out here. I don't know. We always talk about swap and drop, but what do you, yeah, no? Yeah. Yeah, you don't write the ones. So that would come over and down. So that's a 1 there. We don't write ones. That would come over and down. We don't write the ones. Okay. So we swap and drop them. Swap them and drop them. Yes, no? Sure. Did you do something different? Tell me. I don't know. Okay. Oh, it's tough to get you to say anything, eh? Except for these two guys. Okay. All right. We use subscripts to indicate how many of each ion is in the compound. Okay. So, for example, how many ions are in the magnesium chloride one here? What do we got here? Again, you're going to need your periodic tables out, by the way. You should have them out every day here because we're going to use them every day. And mine didn't turn out there. So magnesium chloride looks like that there. How many ions are in total here? Well, you need 1 magnesium, yes? What charge does magnesium come in? 2 plus, yes? And Cl comes in a 1 minus, yes? So those are the ions that you're going to have to use there. Remember, if it's a 2 plus charge, we need to have 2 negatives basically to take those electrons. Magnesium, we already know, loses 2. Yes, we already answered that question earlier today. So there's 2 valence electrons. It wants to lose 2. If it's going to lose 2, we need each chlorine to take 1, right? Okay, does that make sense? Questions, anyone? I see some puzzled looks, perhaps. Ask, don't be shy. No one's going to make fun of you. Okay. All right. Okay. Notice that the overall charge of the compound is still neutral. In the space below, show how lithium and oxygen would form an ionic bond and what would the formula of that ionic bond be. All right, so lithium and oxygen. Okay, so I'm going to get you to go ahead. Let's do a little review here. I'm going to stop for a second. You guys go ahead and draw out a Lewis diagram for just lithium for right now. You're going to have to, now remember, we're kind of doing the same thing we did down here on the first page. So that's how we're getting this all together here. So go ahead and draw a Lewis diagram, or, sorry, not a Lewis diagram. Bohr diagram is what I meant to say. You don't know what a Lewis diagram is. Bohr diagram for, the Lewis would be way easier, by the way. But anyway, Bohr diagram for lithium, okay? And let's do a Bohr diagram for oxygen as well, beside it somewhere, okay? So Bohr diagram for lithium, Bohr diagram for oxygen. We did those the other day, did we not? I think so. Okay. Yeah, we did. We did a whole 10 of them, right? Yeah. So lithium. How many protons does lithium have? Somebody? I'm looking at, oh, sure, Haley. 3. How many neutrons do we need to have here? Oh. 4. Okay. And that's your 6.98, yes, or 7 basically rounded up. And of course we need to have 3 electrons, yes? So 1, 2, and 3, okay? Now remember, okay, and this is the important thing here that we always, you know, even in grade 11 chemistry and sometimes even in grade 12, although by then we should probably know, the charge on this current thing that I've drawn up here is what? What's the current charge right here? Yes. Yes, okay. There is no charge on this atom, right? So when we went to the chemistry lab and I cut it open, right? Cut up open lithium, this is a pure lithium atom, yes? Okay. Now, of course, if it could get rid of this 1 electron right here, if it could get rid of this one, it would love to become more stable. But again, if you just have lithium, chances of that happening aren't good because there's nowhere for that electron to go, right? So along comes oxygen. 8 protons, what, 8 jimmies? Toy Story, remember? And we got 2, and we got what? 1, 2, 3, 4, 5, 6, yes? Okay, so a total of 8. Again, this oxygen is neutral. Along comes oxygen and says, geez, I really like to have an extra electron. So oxygen says, I'm going to take your electron, and I'm going to try and fill up my outside energy level, right? Okay. What's the problem so far, though? Now somebody else. What's the issue here now? Oxygen is going to take the electron, and then what? Right. So what do we need here in this case? What else do we need here? Now, you may have not done this yet, and that's fine. Is it balanced out? Yes or no? This would become lithium 1 plus. This would become what? O, right? But is oxygen stable? What else do we need? Somebody else. What else? Come on. MT, what do you think? Another lithium, okay? So we're going to have to, if we want to fill up that other energy level there, we're going to need to have another lithium. So this one has 2, and again, we have 1, yes? Okay, valence electron, and that one can now go to there, yes? So we need 2 lithiums to go with 1 oxygen, okay? And of course, I think you're gonna have to do this for some homework here eventually. Those 2, remember, they have to kind of balance out. We're looking to make full outside energy levels. You might say, well, if lithium, if the 1 electron comes over here, that's okay, but then there's still, this one only has 1 here. It still needs another one, right? So where's it going to get another electron from? Well, another lithium probably, okay? You have to remember that we probably have millions of lithium atoms in this case, right? So putting that all together, what does that look like? Well, this one loses 1, that one loses 1, that one's going to gain what? Actually 2, yes? So if I go back to here now, and you guys can write this down, 4 neutrons. Now it has 2 and a 1 plus charge, yes? So lithium loses that electron. We have 3 protons, we only have 2 electrons, so it loses 1. This lithium here, and 4 neutrons, loses 1 electron, yes? And the oxygen had 2, 3, 4, 5, 6, had 6, has gained 1, 2, yes? And that becomes a 2 minus charge. And again, remember, lithium, okay, the 1 plus, lithium's a 1 plus, oxygen's a 2 minus. Overall, these are neutral, of course, when you put them all together. All right? Yep. Yep. Nope. Yep. Okay. Good. Yes. For this. So now you might say, okay, well, you know, again, if you look up on your periodic table, if you look up the 2 charges that go with these, oxygen can gain 2 because it has a space for 2, right? Lithium has a 1 plus charge. If you swap and drop these, right? So take the 1 over and down, take the 2 down, we get Li2 and O. We don't write the 1, of course, right? So that becomes lithium oxide. That's the formula. We need 2 lithiums to go with 1 oxygen. Yeah? And that's where the formula comes. That's where swap and drop comes from, basically, because we're looking at the 2 charges, the ratio of how many this one loses, how many this one gains. Yes? All right. We did that. We did the formula. Good. Now, just a little thing that's a little bit important here is that, you know, when we talk about these ions combining together, we're not just talking about 1, okay, or 2 oxygens or 2 lithiums or whatever the case might be. The ions group together in an organized array called the crystal lattice. Make sure you know that. Okay. The overall charge of the crystal lattice will be neutral. It'll be neutral. So if you look at this kind of cubey looking thing here, this is neutral overall. Okay. It's made up of individual ions that have joined together. Opposites attract is really what's going on here. And it's just this positive, negative cube, okay? So if you want to think of it this way, these would be the positives here. So whatever those are, Okay, and it could be lithium, it could be magnesium, although it would be a 2+ charge, but whatever. And these would be all the negatives here. Okay, and they would arrange themselves. Now, that's not maybe the best diagram there, but they would arrange themselves into this cubey-looking structure, which is called a crystal lattice. It's an alternating arrangement, three-dimensional, of plus minuses. Okay, if you looked at your table salt at home, sodium chloride, this is exactly what you would see on an ionic level. Okay, on an atomic level. So it they all form this. Every ionic compound forms this. It doesn't matter really what the ratios are. They form this kind of structure, a crystal lattice. Alternating positive negatives, that's all you need to know, really. Okay, good? I talked for